In the last video, I was talking about frequency domain analysis, and this was just for a review. And in this video, I will be continuing with that. But first, let me just make a definition of robustness. This is the robust control course, and we should have a clear understanding of what we mean by robustness. Okay, so I've collected some critical information here, so let me just go through that. A successful design control system should be always able to maintain stability and acceptable performance in spite of uncertainties. So when we design a controller, we have two main goals. So one goal is to ensure that our system will be stable in the end. And of course, stability is necessary, but it's not sufficient. You may have a stable system, but you may not be happy with how it performs. So the performance is also critical. However, satisfying stability is handled separately, because if you want to ensure stability, it's sufficient if you make sure that all the poles are on the left half plane. But having all the poles on the left half plane doesn't guarantee you good performance, so you have to deal with performance separately. So that's why we specify these separately. So first goal is to make sure that the system is stable. And next, our goal is to make sure that the performance will be satisfactory. Okay, so these two are the objectives when designing a controller. So when we talk about robustness, so these two will be satisfied in spite of uncertainties. So even when there are uncertainties in the system, we want to guarantee that our system will remain to be stable and it will have acceptable performance. Okay, so now the next question becomes, what do you mean by uncertainties? So when we speak about uncertainties, they are generally categorized into two groups. So the first one is the disturbing effects that come from outside. So these are external disturbance signals that may be acting on your system. So these are external disturbances due to like physical disturbances. In the case of an aircraft, this may be atmospheric disturbances like wind gusts and other atmospheric effects that disturb your aircraft, or it may be the disturbances coming from your sensors. So the sensor noise is an external signal acting on the system. Okay, so this is one class of uncertainties that come from outside your system. And the second group of uncertainties are the ones that are present within your system. And these may be separated into several groups as you see here. So the first one is the differences between the mathematical model used for design and the actual system. So when you're designing a controller, you use a mathematical model for your system. And obviously, your mathematical model will never 100% represent the actual system. So you make some assumptions when writing the equations, and you may neglect by choice, or there may be some effects which you cannot mathematical model. So these differences will be a source of uncertainty in your model. So next one is neglected dynamics. So this is different than the first bullet, because here you neglect certain dynamics altogether. And good examples are given here. The flexible modes. So when you are designing a mechanical system, there may be certain parts with flexibility, and when you neglect that, your mathematical model will be of lesser order. But at the same time, these additional dynamics from those flexible modes will be neglected. And also in aerospace engineering, we most of the time neglect actuator dynamics. So when you're controlling an aircraft, you do that through use of aerodynamic control surfaces like elevator, aileron, rudder, and those have their own dynamics. So they are actually second order systems. But usually most of the time these dynamics are a lot faster than the dynamics of the aircraft itself. So it is usually a very good idea to neglect these dynamics. But nevertheless, these dynamics are present in the system, and when you neglect them in your mathematical model, this will also represent an uncertainty in your system. So the next one is neglected non-linearities. So obviously your mathematical model will be linear. but we know that in reality, there's really no system which is absolutely linear 100%. So any non-linearity present in your actual system will be neglected in your mathematical model. So this also brings an uncertainty to your system. So the errant plant parameters, this is another source of uncertainty. So again, if you're designing a controller for an aircraft, you use certain values for the system parameters, like the mass of your aircraft, the moment of inertia values, of center of gravity location. You have certain values, but for the real aircraft, these numbers will never be 100% accurate. So any change in the mass of the aircraft or moment of inertia values, center of gravity, so any differences in those numbers will be additional uncertainties in your system. And the last item I have here is changes in plant parameters. So these will also represent uncertainty. Again, in the case of an aircraft, while flying, if the center of gravity location changes, your model will not be using these varying values. So in that case, those changes will also represent an uncertainty in your system. When you say your goal is to design controllers that will maintain stability and will give good performance in spite of uncertainties, two questions automatically come to mind. The first one is, how do you measure performance? We need to have some numerical assessment of performance. When designing a controller, when you look at how it works, and you say, okay, this looks like good, it's not acceptable for designing controllers. You need to have a numerical measurement of how good the performance is so that you can work on making it better. So when you have a numerical assessment, you can try to make it better through some optimization studies. So that's one thing you should have. You need to have a good way of measuring performance. And the next thing is, you also need to have a way of quantifying uncertainties. We listed a number of uncertainty sources, and for each and every one of those uncertainties, you need to have a numerical measuring method. So when you design a controller, you should say, well, I reasonably expect my model to have this much uncertainty in this parameter, so that I should design a controller so that in all expected situations, it will be able to satisfy its performance and stability properties. So these are the two things that we will talk about in this course. And I can say that this quantification of uncertainties is perhaps the biggest challenge in robust control. So this is really a difficult task because you have multiple sources of uncertainties. I mean, if you only had just one source of uncertainty, if mass was the only uncertain parameter, then designing a controller for that single source of uncertainty would be relatively easy. But when you have simultaneous uncertainties coming from separate sources, it is very, very difficult to take into account all those different uncertainties without introducing too much conservatism in your design. So we'll be talking more about these issues in the later weeks. Okay, so having made this definition of robustness and explaining a little bit what we do in robust control, let's go back to what we were doing in the previous video. So in the previous video, I was talking about frequency domain analysis, and I explained that when you give a linear time invariant system a sinusoidal input, the output goes through some transient, and at steady state, it represents an oscillating output, if provided that system is stable. But when you look at the oscillating signal at the output and compare it with the input oscillatory signal, they have the same frequency. However, the magnitude and phase of the output will be different. And this difference depends on frequency. So when you repeat this exercise at several frequencies, you observe a different magnitude and phase variation. And when you plot them as a function of frequencies on two separate charts, you obtain what is known as a body diagram. Okay, so in a body diagram, you give an oscillatory input. Let's say this is your frequency. You calculate or measure the change in magnitude and phase, and you plot them here, and you repeat this for a number of frequencies, and this is how you obtain this chart. So in Nyquist plot, we represent the complex number which is obtained by the magnitude and phase values for frequencies on a complex plane on a single chart. So let's take a look at this number. So this has a certain magnitude and phase. So you come back to this complex plane, and the magnitude is the distance of that point with respect to the origin, and the phase is the angle it makes with the positive real axis. So we have a negative phase angle here, which is why this point is below the real axis. So the positive would be here. So that's that point. And you take a look at this point, which has slightly higher magnitude. And the phase angle there is minus 90 degrees. So that red point corresponds to this point here. Okay, so this distance again is 2, and that corresponds to this in decibels. So this point corresponds to this frequency value. Okay, so which is 1 radians per second. So on the Nyquist plot, every point corresponds to a point on the body diagram and has a certain frequency. So for this particular system, when you go through all this frequency range, this is what you obtain. And the upper part is symmetric of that, and that is for negative frequencies. So on body diagram, we only see positive frequencies, but for the Nyquist plot, you plot the output of the system both in the negative and positive frequency interval. The Nyquist plot or Nyquist diagram has certain advantages over the body diagram in terms of determining the stability of the closed-loop system and how far the system is from being unstable. So in other words, it gives the safety margins in terms of certain measures. Well, I think the body diagram can also give you the stability margins provided that the open loop system is stable. But in the case of Nyquist diagram, even when the open loop system is unstable, you can still conclude the stability of the closed loop system and its stability margins. Well, if you are curious about this difference, I can provide you to some references where you can read more about the details. But the Nyquist diagram is more powerful in terms of assessing the stability and robustness of the system. Okay, so let's remember some details about the Nyquist plot and Nyquist stability test in particular. So for that, let's consider this general block diagram of a feedback control system. The closed loop transfer function of the system can be obtained as you see here. Remember, this was defined as the loop transfer function previously. Okay, so obviously for the closed loop system to be stable, we know that all the poles of this transfer function or all the roots of this part should be on the open left half plane. So when you have a root locus, you directly see the locations of the poles. You see where the poles are distributed on the complex planes, so that you immediately see whether the system is stable or not by just seeing the locations of the poles. However, in that root locus, you can't really see how close the system is to becoming unstable. Well, the Nyquist plot gives you some nice measures of that. So let's remember how you do that. Okay, so first of all, in the Nyquist plot, you draw the plot for the loop transfer function and not the open loop, not the closed loop transfer function. I'm sorry. So you draw the plot for the loop transfer function, and when you do the plot, So these are important. Z is number of poles of 1 plus GL in the right half plane. In other words, Z is number of unstable poles of the closed loop system. So obviously for stability, we want Z to be equal to 0. Okay. Then P is the number of poles of GL in the right half plane. So this is your loop transfer function. And P is the number of unstable poles of your loop transfer function. So this doesn't have to be 0. Your open loop system may be unstable, in which case GL will have those right half plane poles. And how many of them gives you this P number. Next, N is number of clockwise encirclements of the -1 plus 0j point on the complex plane by the Nyquist plot of GL. Okay, so if you come back here in our example, the -1 plus 0j point is this one. So in this example, there are no encirclements. But for certain systems, you may observe some encirclements of the -1 point, and you just count the number of clockwise encirclements for the entire Nyquist plot, and that will give you that n number. Okay, now the Nyquist stability criterion states that Z is equal to n plus P. So without closing the loop, you already know the number of unstable poles of the loop transfer function. You know what P is. And when you draw the Nyquist plot, you can count the number of encirclements, which will give you the n number. And adding these up will tell you if your system has any unstable poles in the closed loop or not. So if that turns out to be 0, then you're good. Then you can say that your system is stable. The closed loop system is stable. I think the best way to understand how Nyquist stability test works is to see that on an example. So let's take a look at this example. So we have chosen some transfer functions for the plant, and this is our sensor, and the controller is just a static controller with unity gain. The loop transfer function is obtained by multiplying all these transfer functions, which gives you this transfer function. And there are 3 poles, and all these 3 poles are stable. So they are all on the left half plane, which says that P is equal to 0 for this system. Okay, so by just looking at the poles of the loop transfer function, we see that P is equal to 0. Next, we draw the Nyquist plot. MATLAB has a function that will directly do that. Well, in this chart, I did that manually. I just obtained this plot by manually calculating the response of the system and then creating this plot because I want to be able to have more control over the plot. And this is what you have. So the chart starts from here and then goes all the way up to that point for positive frequencies. And for negative frequencies, you have the other part. And as you see here, the -1 point is there. So the encirclement of the -1 point is actually 0. So we have P is equal to 0. Z is equal to 0 as well. And in that case, well, I think I didn't write that here, but if you go back to that criteria, Z is equal to n plus P, and they're both n and P are equal to 0, and Z is equal to 0 as well, which means the closed loop system is stable. Okay, so at this point, we know that our system is stable without having to calculate the closed loop transfer function. Okay, so next, let's talk about how we can see how far this system is becoming unstable. The closed loop system will become unstable when it has poles on the right half plane. So when you come back to this analysis, if we have Z is equal to a number greater than 0, that will indicate an unstable system. but z is equal to n plus p. So assuming that the number of unstable poles of the open loop system remain the same, so in other words, p is equal to whatever it is previously, for z to become a positive number, n needs to change, and n is the number of encirclements of the -1 point. Okay, so the system becomes unstable if the Nyquist plot, however, starts encircling the -1 point for this particular example. We have the mathematical model for our system, and this mathematical model is characterized by its transfer function, and there are two parameters that characterize that transfer function: its magnitude and phase. And we see this on the body diagram, right? So if you have an uncertainty in the system, then this uncertainty will cause some changes in these parameters, right? So the uncertainty will either cause some changes in the magnitude, or it will cause some changes in the phase plot. So let's talk about how these changes can lead to instability. So let's start with the uncertainty in the magnitude. Okay, so consider that your model gets an coefficient a. Okay, so this a is an unknown coefficient. So, and this will cause the entire magnitude of this transfer function to change at all frequencies. So let's see how these body and Nyquist plots change for different values of a. So when a is equal to 1, this is our nominal system. A is 1 is the nominal system, and the nominal magnitude plot is this one, and the phase plot is shown here, and the black one is the nominal plot, Nyquist plot for our system. So if a is a number greater than 1, it will cause an amplification. So we see the effect on this magnitude plot here. The plot shifts upwards to this red one. Well, it doesn't cause any change in the phase. So the phase of the amplified plot is exactly the same as the original plot. But when you look at the Nyquist chart, the magnitude of every point is increased. So if you have, looking at this frequency, you multiply it with a constant number, which positive number greater than 1, which brings you that point. And that shift occurs at every frequency, which means the entire Nyquist plot will grow. On the other hand, if a is a positive number less than 1, in that case, it will cause a reduction of the magnitude. On the body plot, you see that the magnitude plot is shifted downwards to this blue one. Again, there's no change in the phase plot. And on the Nyquist plot, this time for every point, the magnitude is reduced by a certain scalar, the same scalar at every frequency, which means the entire plot will shrink to this blue curve. So for values of a that are less than 1, there's no danger, because a value of a less than 1 will make the chart smaller. And if you come back here, the original Nyquist plot doesn't encircle the -1 point. And as it gets smaller, there will be no encirclements. So this means that for smaller values of a, or in other words, if the magnitude of the system is reduced, then the closed-loop system will remain to be stable. But for greater values of a, which means if the magnitude of the system is increased, then you have to be careful, because as the Nyquist plot grows, at some point it will cross the -1 point, and as it passes it, for values of a that are greater than that critical value a star, there will be encirclements of the -1 point, which will make the closed-loop system unstable. And we see that here. So this is the critical value of a star, where the Nyquist plot crosses the -1 point. In fact, it crosses it twice. And so this is the border of instability. So for this particular value of gain error, the system is at the verge of being unstable. And if you increase a little bit more, the part will turn into this one, where now there are encirclements of the -1 point. In fact, it encircles it twice. So let's see how we can conclude that. So draw a straight line from -1 through somewhere outside the Nyquist plot, and see how many times that straight line crosses the Nyquist plot. So there are 2 points where it crosses it, which means the encirclement is twice. And these encirclements are clockwise encirclements, by the way, because we know that the plot starts from here and moves in that direction. So it encircles it once, and it encircles it one more time, and the total encirclement is 2 for this particular example. Okay, so the question is, what is that critical value of A star? And we can see that very easily from the original chart. So you find this point where the Nyquist plot crosses the negative real axis, and that point is the point where the phase is minus 180 degrees, or it's negative pi in terms of radians. So at that point, at that frequency where the phase is that much, you look at the magnitude of the system, and obviously you can read these values from the body plot as well. And if you check the find that magnitude, and the inverse of that magnitude gives the critical value of A star. Okay, so we call that critical value the phase margin of the system. And this is how we can find when a change in the magnitude of the system can cause instability. Okay, so next let's talk about how we can find when an uncertainty changes the phase of the system rather than the magnitude. Okay. Consider the phase of the system is shifted by an amount phi at all frequencies. So in other words, take the original system plot and shift every point on that plot by an amount phi. So let me just show that here. So let's just use it on the original plot. Okay, so take this point. Okay, so my pen stopped working again. Okay. So this is the point, and it has an original phase angle of that much. You shift it by a certain amount phi. So let's say this is the phi angle. Okay, so you take that point and move it to that location. And take another point, this one for instance, and shift that point, or which shift means rotate it by the same angle phi. So you take that point and shift it to that point, and you repeat this for every point on the chart. In the end, the entire curve will be rotated by that phase angle. Okay, so let's see what the effect of that will be on the stability. Okay, so this is here you see the shifted version. And on the body part, an error, a constant error in the phase will cause a change in the phase plot, obviously. This time, the magnitude plot doesn't change. So there are two systems here. One is the original system with no phase change. And in the second part, which is shown with the red, there's a positive phase error in the system. So again, the positive phase error causes the phase plot to go down by that amount. And when you come to the Nyquist plot, it causes the entire plot to rotate. Okay, so just like in the magnitude case, as you keep turning the plot, at some point it is quite possible that the -1 point will be encircled because of this rotation. And again, there's a critical value there. So until that critical value, the encirclement is the same. So the stability is the same. The original was stable and it remains stable. But when you hit that point, after that point, it will be encircled. -1 point will be encircled, and the system becomes unstable. So now the question is, how do we decide what that critical angle is? And it is quite easy to see that angle. Let's come back to the original plot here. And now here we added a unit circle centered at the origin, shown with this dashed line here. And that you find the point where the Nyquist plot crosses that unit circle, which is this point here. The system or the encirclement will change when rotated by that amount. And this angle is, you see here, is the critical value for phase before the system becomes unstable. Okay, so this is how you find this critical angle, which is the phase margin. Again, you draw a unit circle and find the point where the Nyquist plot crosses that unit circle and measure that the angle between that point and the negative real axis. So this is the critical value, and here you see the curve that is rotated by that amount, and at that point this is the border of stability for this example. And if the rotation is any bigger, or the phase is shifted by a bigger amount, the -1 point will be encircled, and the encirclement is 1 here. So when you increase the phase of the system by this amount, after that point, the system will have one unstable pole in the closed loop. In the case of gain, the encirclement was 2. So which means when you make the system unstable by increasing the gain, after you hit that gain margin, the system gets 2 unstable poles. But in the case of phase uncertainty, when you hit the phase margin, the system gets 1 unstable pole in the closed loop. And we can decide that by counting the number of encirclements. This is how we can find gain and phase margins using the Nyquist plot. But remember, when we did that, we assumed that whenever there was a gain error, that error was effective in the entire frequency range, which means the entire plot was growing or shrinking. However, what determines stability, or what makes system unstable, is the growth at this point only, right? So the system becomes unstable only when this point grows by a certain amount. So in other words, if the plot at this point grows by a different amount, it doesn't affect stability, as we see here. So what this means is the gain margin is actually associated with a certain frequency. And as we discussed earlier, every point corresponds to a frequency, and whatever frequency this point corresponds to is the frequency that corresponds to the gain margin we found. A similar argument can be made for the phase margin. Okay, so the phase margin is determined by this point, right? And this point corresponds to another frequency, and whatever that frequency is, only when the system is rotated or the phase is shifted by a certain amount at that frequency, the system becomes unstable. So just like the gain margin, phase margin also corresponds to a certain frequency. And whenever you mention gain and phase margins, you always have to give the frequencies as well. Otherwise, just the gain margin by itself without the frequency information doesn't really tell the whole story. And for the phase margin, it's even more important. So in terms of angle, your system may have a very large phase margin. But if that phase margin occurs at a very high frequency, then from a practical point of view, the benefits may not be that much. Let me explain what I mean by that last statement. The phase uncertainty will be caused by a certain dynamic uncertainty. You know, whenever you have a dynamic uncertainty, that dynamic uncertainty will have its own magnitude and phase characteristics, just like the transfer function of another system. And these magnitude and phase characteristics will be shifting the magnitude and phase of the system. But from a practical point of view, perhaps another even more important concern or uncertainty is time delay. So by the way, there are these explanations here. So if you are taking this course, you have already these lecture notes, so you can study this, read through these lecture notes. I try to explain everything as much as I can. And I'm not going to obviously read through these explanations in the video, so you can read them yourselves. So anyway, let me come back to this concern for time delay. Okay, so a phase error at a certain frequency corresponds to a certain time delay, and consider a phase margin of phi star at frequency omega p, and we can find the corresponding time delay as you see here. So the phase margin occurs at a certain frequency, and this is the border for instability. But you can write this in terms of time delay instead of phase error. You can write this exact expression using time delay. How you do that? You add this uncertainty to the time value, not the angle. So this is the angle, and here the uncertainty is added to the angle. But in next case, I write it in terms of frequency times time, and the uncertainty is introduced next to the time. So by equating these two, I can find what TD is, and TD turns out to be this much. Okay, so you find what the phase margin is and divide it by the corresponding frequency, and this operation will give you a quantity with the units of time, and that will give you the time delay margin. So in other words, without any dynamic uncertainty in the system, if you have time delay in the system, which you will have in a real system, due to how the system is designed, there will inevitably be some time delays, right? So this can be due to the sampling rate, how frequently you make the calculation, how frequently you measure your sensors. There will be some time delay in the system. And if the time delay is greater than time delay margin, then the system will be unstable, even if you have no other uncertainty, even if you have no dynamic uncertainty, no gain uncertainty. If the time delay is greater than time delay margin, you will have trouble. Okay, so let's take a look at this particular example, and these are the numbers. The gain margin is 1.6259, and the corresponding frequency is what you see here. The phase margin is about 36 degrees at 0.9881 radians per second. And using these numbers, we get the time delay margin to be 0.6350 seconds. In the earlier videos, I told you that in robust control, we sort of combine the benefits of classical control and modern control. In classical control, we have some powerful frequency domain techniques, and this is really what I was meaning by that. So we can assess the uncertainty or robustness of single input, single out systems using this Nyquist stability test. But here we cannot really study multi-input, multi-output systems, right? So this is only true for single input, single output systems. And in modern control, we use state space representation where we can handle multi-input, multi-output systems easily. But here we don't have such easy ways of checking the robustness of the system. And in robust control, we combine the benefits of these two. So that means in this course or in robust control, we will be utilizing this Nyquist stability test for multi-input, multi-output systems. So at this point, I recommend that you make sure that you have a good understanding of Nyquist plot and the Nyquist stability test, the example that we did here. So if you have any doubts about this example, please go back to your classical control book and study the Nyquist plot and Nyquist stability test again, and that will be useful for this course. Okay, so let's stop this video, and in the next video we will continue with internal stability and how state space approach or state space model is better than the transfer function model, and we will continue with the state space representation.